This is HRW911P060. So it says in the figure below, a bullet is fired into a block attached to the end of a non-uniform rod of mass. They give you the mass. The block rod bullet system then rotates in the plane of the figure about the axis A. The rotational inertia of the rod alone about that axis, and they give it to you, treat the block as a particle. So first they want, what then is the rotational inertia of the block rod bullet system about point A? So that's the easiest part. Let's see, change that. They already gave you the rotational inertia of just the rod. You just need to do the block and the bullet and add those together. So like the total rotational inertia of the whole system is going to be the rotational inertia of the rod plus the rotational inertia of the block plus the rotational inertia of the bullet. Those are both B's, aren't they? Block. Okay, I'm using B, capital B for the block because it's bigger, and lowercase b for the bullet because it's smaller. Okay. All right, I already have IR. So IB, the block, they said to treat it as a particle. So the rotational inertia of any particle, okay, so we've got IR. For any particle, rotational inertia is just mr squared, okay? So we just need to put in the m of the block and the r of the block, and then we should be fine. So, well, the m of the block is, they give that to you. They have a 30 kilogram block. So I'm just going to put mass of block, because your mass will be different than mine. Okay, and then R, well, R is how long the rod is. It's a 0.6 uniform non-uniform rod, so that is the that's the radius, which that is not a red number. No, it's not. So that means it should be the same for everybody. Okay. So I'm just going to go ahead and put it in. Alrighty. And then that's got to be squared. Then we need the bullet. Now, we are concerned with when the bullet goes into the block. So the bullet is also 0.6 away, and it's also a particle. So we're going to have the mass of the bullet times 0.6 squared will be our wow, I need to go to bed. It's really tired. It'll be our rotational inertia. Yeah, moment of inertia for the bullet. Okay, so if we do all that, we are going to get IR they give us, it's 0.06. Alright, plus for me, where is that? The block is 0.3 kilograms. Okay, so that's me. Yours will be different. And then I've got that 0.6. And then the mass of the bullet for me, I've got 4 grams. I gotta turn that into kilograms, so that's 0.004 kilograms. And the mass of the bullet, or sorry, then the radius that it's away. Okay, and I add those all together, put that in a calculator, and I get 0.16944. So I'm going to round that. While I was typing to my calculator, I noticed that I made a mistake when I was writing. The rotational inertia of just the rod was 0.06, so this should have been, come on, eraser thingy. Come on, hello, wakey wakey. So sorry about that. I didn't notice until I was typing it, and I was like, wait a minute. Okay, let's see, kilogram meters squared. Okay, so that's my answer to A, and that is in fact what the key says, so that we're good there. Next we want, if the angular speed of the system about A just after impact is 4.5 radians per second, what is the bullet speed just before impact? This is a conservation of momentum problem. Usually what we do is we find the total momentum before a collision, and then that equals the total momentum after the collision. We find something out after the collision. But it works the other way too. I can find, with this information, the total momentum after the collision. that should be the same as the total momentum before the collision. So after the collision, the total momentum is, well, I've only got this one thing spinning. So that one thing spinning, angular momentum, remember, is, oops, and then I used the wrong symbol, sorry. Angular momentum is moment of inertia times rotational velocity. So we just found the moment of inertia of the whole thing. So I've got that, and then they tell you that that whole thing has a angular speed of 4.5 radians per second, which means that the total angular momentum of this system is, let's see if this is just still in my calculator. It is. I'll just go ahead and type it without pausing. Here we go. 0.76248. I'm not going to round it right now because we're not done yet. So that's my total momentum. I know that in the absence of outside torques, and there weren't any outside torques of this rod block bullet system, the total momentum had to stay the same. So this total momentum has to be the same before the collision as well. So if you think about this, before the collision, the rod and the block were not moving. The only thing that was moving was the bullet. So the this should be just the momentum of the bullet before the collision as well. Okay? Just the angular momentum of the bullet before the collision, which is the rotational inertia of the bullet times the initial angular velocity of the bullet. So bullet, well, we're assuming this bullet is like immediately right before it hits the block. So it's like right here. Can you see where our mouse is? Right there. So I still have that same mass at that same radius. So I of the bullet is still what it was in the last section. Okay. So that was what, 0.004 times 0.6 squared. Okay. That means all I gotta do is divide by that to find the original angular velocity. So that's gonna be, what is that, 0.76248 divided by 0.004 times 0.6 squared. Okay. So that's gonna give me angular velocity, and I get, hang on, I can just do this. Alright, that gives me 529.5 radians per second. And then finally, they want the bullet's speed. Notice they didn't put the word angular in there. If they don't put the word angular or rotational or circular or something like that in there, they want linear. So they really want linear velocity. And linear velocity, as I'm hoping you know by now, linear velocity is angular velocity times r. So I just found angular velocity of the bullet before. That means my initial linear velocity of the bullet is going to be 529.5 radians per second times the radius, which was 0.6. Okay, so if I do that, just put that in there really quick. 0.6, there we go. I get 317.7 meters per second, as long as everything was in radians and seconds and everything. And we'll check. They rounded up to 318. That's good, but that's the answer.